All right, so we're finally ready to derive this complex roots theorem. In order to derive y, the solution is y equals k1 e to the at sine bt plus k2 e to the at cosine bt has to do with the superposition theorem and as well as the linearity principle. All right, so in order to use this, we have to use Euler's identity, which says that e raised to the theta I is equal to cosine of theta plus I sine theta. So let's just say that our roots that we get are a plus or minus bi. So that means we're going to have two solutions. We're going to have y1 equals e to the a plus bi, and y2 is going to equal e to the a minus bi. Now that's all fine, right? That is the solution. Oh, I'm sorry, times t. It's our root times t. And that is our solution, but the problem is we have an imaginary number in there. So you can't really go and graph this on a real number plane. Now using properties of exponents, I can break this up into e to the at times e to the bti. All right, so distribute the t in, you get at and then bti. And then by property of exponents, we know that if you have common bases, you can add their exponents, but you can also work backwards and split it back up into two factors, which is what we're doing here. I'll do this in tandem because this is going to be the same process, except this will be e to the at times e to the negative bti. And so if we believe or trust Euler on this famous identity, then that means that e to the theta I, this bt is like our theta, and so if we apply this identity to just this second factor here, we're going to have e to the at times, and so again our theta is this bt right there, so that whole thing will expand into cosine of bt, and you can kind of see where that cosine and sine of bt are coming from, plus I times sine of bt. And the same thing will apply over for y2. That will be e to the at, but multiplied by cosine of negative bt plus I sine of negative bt. So there's our y1 and there's our y2. Now again, they still involve imaginary roots, but at least the imaginary number is no longer in an exponent. So that's one of the advantages of Euler's identity, is it allows us to take the imaginary number and write it as a coefficient instead of as an exponent. Okay, so here's what we're going to observe. We know that, first of all, also here, cosine of negative bt from an identity that we know in trig, or that we maybe don't remember all that well, is that if you have cosine of a negative angle is equal to cosine of the positive angle. So if here is a theta, and that value right there is going to be the same thing, same value as negative theta, which would be that guy right there. So by that identity, e to the at, cosine of negative bt is the same thing as cosine of positive bt. bt is just the name of the angle. Sine, on the other hand, looks like this. So for the positive theta, you have some number, but then for the same but opposite theta, you have the negative of the number. So that means that sine of negative bt will be the negative of the sine of positive bt. And so what that does is now we see that these two solutions are very similar. So we have y1 equals e to the at cosine bt plus I times e to the at sine bt. And our second solution here, y2, is equal to e to the at cosine bt minus I e to the at sine bt. So those are our two solutions, and still they have that imaginary number in there. But what the linearity principle tells me is that any combination of two solutions, any linear combination of two solutions is also a solution. So that means if I take these and I combine them by scaling and adding them, then I will be able to come up with another solution. So let's call this y1 star. And that star is just going to indicate this is going to be our brand new y1. And what I'm going to do is to create that, I'm going to take 1/2 of y1 and add 1/2 of y2. Now, why did I pick a half? Well, you'll see in just a moment what happens when I pick a half. So 1/2 of this guy plus 1/2 of this guy will give me 1/2 e to the at cosine bt plus 1/2 of this. And when I add these two together, because this will have a 1/2 and this will have a 1/2, they will add together to give us a whole e to the at cosine bt. And whenever you take 1/2 of this plus 1/2 of this, notice that they're equal but opposite signs, so that will give us plus 0. And so our y1 star has successfully eliminated the imaginary number. Now, there's nothing wrong with doing that. An imaginary number still acts and is treated just like a constant. So just because you see an I in an equation does not mean that it precludes the use of regular mathematics. Now, y2 star, I'm going to take another combination of these. I can't do the same thing, but if I play this little trick and I take 1 over 2i times y1 minus 1 over 2i times y2. Now, 1 over 2i is a constant. It's perfectly fine to use that. Let me go ahead and actually plug these in. So if I take 1 over 2i times this, I get 1 over 2i times e to the at cosine bt plus 1 over 2i e to the at sine bt. Now I'm going to take minus 1 over 2i times this, so I'll have minus 1 over 2i e to the at cosine bt. So that's just negative 1 over 2i, that term. Now minus negative 1 over 2i times this term, which will give me plus 1 over 2i, because now I'm scaling a negative by a negative 1 over 2i. Let's give me plus 1 over 2i I forgot my I here. I e to the at, I e to the at sine bt. And now when I add these, we notice that these two cancel. And what happens with these last two terms is here the I and the I cancel, and the I and the I cancel, and I have 1/2 of this plus another half of that just gives me e to the at sine bt. And this is what we're calling y2 star. Now, again, we can keep using this linearity principle, and we can say, well, we formed two new solutions that just don't have any imaginary numbers in them. So my general solution, let that be some constant times y1 star plus some constant times y2 star, and that comes out to k1 e to the at cosine bt plus k2 e to the at sine of bt. And we just have them mixed up with the k1s and k2s, but you notice this is exactly the same solution that we claimed was the solution to a system with complex numbers. So this is why I waited till the end. It gets a little tedious with some of the algebra, but it's a really beautiful process. And it takes advantage of theorems. And this is kind of what we do in mathematics. We try to utilize old things to help us devise and solve new problems.